Ionization smoke detectors are very common. They're used in homes, schools, workplaces, and around the world. What makes them special is that they use a tiny amount of radioactive material to sense smoke. That material is called americium-241, a synthetic element that was created in nuclear reactors. Americium-241 undergoes a specific nuclear reaction called alpha decay. In alpha decay, the nucleus emits an alpha particle, which is basically a helium-4 nucleus, two protons, two neutrons tightly bound together. Now, this type of radiation is used in the detector is called alpha radiation. As for the activity of the americium source, a typical ionization smoke detector contains about 0.9 microcuries of americium-241. Basically, that's about 30,000 decays every second. That may sound like a lot, but in the world of nuclear physics, it's actually a very small amount. Each alpha particle carries about 5.5 MeV of energy, which is enough to ionize air molecules, but not enough to penetrate even a few centimeters of air. So, how does this radiation help detect smoke? Inside the detector is a small ionization chamber. It contains two metal plates with a voltage applied between them. Under normal conditions, the alpha particles emitted by the americium collide with air molecules in the chamber. These collisions knock electrons off the molecules, creating positive ions and free electrons. Because of the electric field between the plates, these charged particles will drift towards the opposite sides of the chamber and form a tiny but steady electric current. Now, this current is very small, way too small to feel, but the detector's electronics are designed to monitor it continuously. The key point is that the detector does not measure radiation directly. Instead, it measures the ionization effect the radiation produces in the air. This is an indirect detection method, but it's extremely reliable. Now, if we imagine smoke entering a chamber, the particles are large compared to normal air molecules, and they tend to sort of attract and capture the ions created by the alpha particles. When these ions stick to the smoke particles, they become neutralized and can't carry charge anymore. As a result, the ionization current drops, and the detector circuitry is designed to recognize the exact instant that this drop happens. So as soon as the current falls below like a certain threshold, the detector interprets it as the presence of smoke and triggers the alarm. This brings us to the question, is radiation safe? The answer is, well, yes. Here's why. Alpha particles have a very low penetration power. They can be stopped by a sheet of paper, or the outer layer of your skin, or even a few centimeters of air. The americium source in a smoke detector is sealed inside a metal foil which prevents any possibility of inhalation or direct contact. The radiation that escapes the sealed source is a tiny amount of low energy gamma radiation, and even that is far below the natural background levels. In fact, standing next to a smoke detector for an entire year exposes you to less radiation than if you ate a few bananas or even took a cross-country flight. If it's at the microscopic level, the individual americium nuclei undergo alpha decay. Each decay event produces one alpha particle. The alpha particle travels a short distance, and a long distance it collides with the air molecules and creates a bunch of ions. These ions contribute to a measurable current. As soon as the smoke enters the chamber, it disrupts the ion flow. The electronics detect this disruption, and the tiny change originating from the individual nuclear decays ultimately trigger a loud alarm that will wake up everybody. In other words, the process that's happening on the scale of femtometers, the size of an atomic nuclei, ends up producing a signal on the scale of meters, the size of your living room. It's cool to see how examples in physics connect the smallest building blocks of matter to everyday technology. So in summary, ionization smoke detectors use americium-241, which undergoes alpha decay. The radiation is involved in alpha radiation, which is a typical activity, about 30,000 decays per second, and an energy of about 5.5 MeV per alpha particle. This detector measures the radiation indirectly by monitoring the current created in the air. Smoke reduces current, causing electronics to detect it. The radiation is safe because the alpha particles can't even penetrate your skin or a piece of paper. And finally, the microscopic nuclear process of alpha decay leads to the macroscopic event of a smoke alarm sounding.
So to begin with, which is how the radiation is produced. Microwave radiation in a microwave oven is produced by a device called a magnetron. Inside the magnetrons, electrons are accelerated by electric fields and forced into curved paths by magnetic fields. These accelerating charges oscillate and emit electromagnetic radiation. For the physical process, here is a radiation from oscillating charges, not nuclear decay or atomic electron transitions. This is a purely electromagnetic process. For the type of radiation, the radiation produced is microwave radiation, which is part of the electromagnetic spectrum. It is non-ionizing, low energy per photon, and long wavelength radiation. So it cannot break chemical bonds or ionize atoms. It only transfers energy through molecular motion. For the frequency, wavelength, and energy per photon, microwave ovens operate at a standard frequency of about 2.45 gigahertz or 2.45 times 10 to the power of 9 hertz. This corresponds to a wavelength of about 12 centimeters. Using the equation E equals H times F, the energy per photon is extremely small, and it is equal to about 1.6 times 10 to the power of negative 24 joules, which is about around 10 to the power of negative 5 electron volts. This means that each individual microwave photon carries very little energy compared to the visible light or UV radiation. For how much radiation is produced per second, even though each photon has a very low energy, microwave ovens produce a large amount of radiation per second. A typical microwave oven outputs about 1,000 watts, meaning 1,000 joules per second. When you divide this power by the energy per photon, you get about 6 times 10 to the power of 26 photons per second. So the heating effect does not come from powerful photons. It comes from an enormous number of low energy photons. How microwave heats food? Microwave heats food mainly by interacting with polar molecules, especially water. Water molecules have a positive and a negative and making them electric dipoles. The oscillating electric field of the microwave radiation forces these molecules to rotate back and forth rapidly. This molecular rotation causes collisions with nearby molecules, and those collisions convert electromagnetic energy into thermal energy, which we experience as heat. So when the heating occurs, it occurs through radiation and then molecular rotation and then collisions and then to thermal energy. This is not ionizing, neither bond breaking, or it's not chemical reactions. It's purely just mechanical energy transfer at the molecular level. Standing waves in the microwave. Inside the metal cavity of the microwave oven, the radiation reflects off the wall and interferes with itself, creating standard waves. These standing waves have high field regions, which are hot spots, and then low field regions, which are cold spots. This is why microwaves heat unevenly and why turntables are used. To move the food through different field regions, so heating is more uniform. The photon energy per versus total power. is more important. This is the most important idea because photon energy is extremely small and total power energy is extremely large. Microwave heat food not because individual photons are strong, but huge numbers of photons deliver energy continuously. So heating comes from quantity of photons, not photon strength. And in conclusion, microwave ovens produce electromagnetic radiation using a magnetron, which generates microwaves through oscillating charges. This radiation has low energy per photons, but extremely high photon flux. The microwave interact with polar molecules like water, causing molecular rotations, collisions, and thermal energy transfer. Standing waves form inside the oven, explaining uneven heating patterns. Most importantly, microwaves demonstrate the difference between photon energy and total power. Individual photons are weak, but massive numbers of them create strong heat. And then I had to create a sketch on this, which I can go right here. And as you can see, the magnetron produces microwaves that form standing waves inside the metal cavity. And when these waves interact with water molecules in the food, they cause molecular rotation that leads to heating, which you can see in the sketch, everything that's happening and all the things that are within the microwave oven.
Hi, my name is Marisol, and I'm going to be explaining and demonstrating how UV light works during security to verify that documents are authentic. Ultraviolet light, or also known as UV light, is used to reveal secret features in documents. Since many security inks, fibers, and coatings are designed to fluoresce when exposed to UV radiation. The UV light used for this purpose is typically in the UVA wavelength range, which is about 315 to 400 nanometers, which has higher energy per photon than visible light. This higher energy allows UV photons to activate electrons in certain materials. What I have here is a UV light, which works the same as a security one, but this is not so professional. These lamps usually operate at a very low power, but they provide enough radiation to trigger fluorescence without damaging any documents once going through security. The fluorescence occurs when a material absorbs UV radiation and re-emits the absorbed energy as visible light. Materials such as brown paper, security inks, polymer threads, and specialized dyes fluoresce because their molecule structure allow electrons to be easily activated by UV light. The emitted visible light makes hidden patterns or markings stand out clearly, enabling document authentication and court-fate defections. So here I'm gonna give a demonstration on how the UV light works with official documents. So with this debit card, where the signature is supposed to go, we really can't see nothing but these lines. But once the UV light is reflected, we can see the brand or the name Visa being like appearing over the card. And even though with the naked human eye we can't see this, once we use the UV light, it is revealed that it's there to see, to prove that the document is authentic. Same goes for a passport. As we can see, we can only see like this little holographic thing and the little design in the back. But once UV light is reflected on it, we can see this pattern in the back of it, which we can also see with the naked human eye.